morning, everybody. So we start this session on Wednesday. First of all, just to remember for those who want credit, to sign the list on the entrance. So we have a pleasure this morning to have our guest, Professor Andrea Camargo. She was a professor here at the Institute of Physics here in São Carlos, USP, and now she's at the BAM, Berlin, and also professor at Otto Schott University in Germany. Professor Andrea is a specialist on characterization of optical materials and also development. She's also worked with luminescent materials, and it's a pleasure to have you here.
Thank you, Francisco. Welcome, everybody, to this third year of lectures. We were actually a little late. We are a little late because we were waiting for some people who had some problem getting here, but we should start now. So again, thank you very much for this opportunity. As Francisco explained, before joining BAM in Germany and also the Jena University, I was for about 20 years in this same institute here, where I took my PhD and was also a professor during 17 years. So on Saturday, you get a chance to visit my lab, which is still active in Campus 2. So we will have a bus, and then Professor Eduardo Bellini will take you there, and we'll make a quick tour of the lab. So you can see here that this is the Physics Institute in Campus 2, and what you see up here is actually the windows of my lab, which is still active, as I said. And this is my research group here. Unfortunately, this is an old photo. Some people have left already, and some have come. Like, I'm not sure if I see Leticia here. Are you here, Leticia? Is this you here? Yes, okay, good. So it seems like everybody's here except those who left. And our main focus of research has been optical materials. And a good part of that is optical glasses, glasses for near-infrared applications such as laser, active media. But lately, we have been very much interested in visible applications. So we have been looking into scintillators, host-gas hybrid materials for lighting devices and sensors and so forth. But we don't do only glasses. We also have expertise in nanoparticles, upconversion nanoparticles, magnetic, and also metallic nanoparticles. And we are also interested in persistent luminescent glass composites, which combine glassy hosts with particles. So this is part of the agenda that we're actually pursuing at BAM now. And then in July last year, I received a very nice offer from BAM and the University of Jena. Actually, I received the offer before, but July last year, I went to Germany to join the team at BAM. So what is BAM? That's a federal institute. It's a senior institution under the Ministry of Economic Affairs and Climate Action in Germany. And our mission is to ensure safety in technology and chemistry. So besides doing research and also advising companies and other labs and technical institutions, we also contribute to guarantee that Germany will be an attractive destination for scientific partnerships. And BAM is divided in 4 locations in the south of Berlin, as you can see here. I marked with the red dots. We are at the Adlershof location here. You can see that there is a dot outside of the map here because it's southern. It's in the state of Brandenburg. And this is where we have the explosive testing facilities. We don't go there very often for obvious reasons. So this is our building here in the Adlershof campus. And what's unique about our division on glass research is that we have a robot. You probably have seen already, my colleagues have already talked about the robot installation we have for the melting of glasses. So the robot does everything from weighting the precursors to casting the glasses and annealing and everything. So we have Christian Meyer here, who is one of the persons responsible for this infrastructure. And this was a project that was started by Ralph Miller. You also heard his talk yesterday. He is my predecessor at BUM. So my particular mission at BUM is to take the leadership on this project here and to ensure that this robot can be used in the frame of materials digitalization. So we want to add artificial intelligence tools to be able to make these robots smarter. And then we can have high throughput glass production for research. And also, my personal contribution is to start now an agenda of optical glasses in the division, which is my particular expertise with what I have been working for many years. So optical properties, this is our theme today. And what is the relevance of studying optical properties of glasses? I don't think I have to make much of an effort to convince you what is the relevance of developing optical glasses, right? So if you just look into these slides here, you can see that from lenses that allowed us to discover microscopic and macroscopic world, we have a number of applications here that you can recognize as being part of our day-to-day routine. Can you imagine life without these things? Your cell phone or fiber optics or the sophisticated exams we can do nowadays because we have photo detectors that are very efficient and so on. So this is the outline of my talk here. First, I will tell you a little bit of the background, right? We have to remind ourselves of what electromagnetic radiation is and how it interacts with matter. And then we go to the optical properties of glasses more specifically. Number 3 will be some techniques. So we'll just take an excursion through the techniques for characterization. And then in 4, I will talk just a little bit about applications, but Professor Marcelo Nalim, who will give the next talk, will go a little deeper into that, so I'm not going to talk so much about properties, just mention a few. And regarding the references for this talk, you can see here some of them. I apologize that I didn't have time to include all the papers that were produced at LEMAF, and I used some figures of these papers, but this will be updated, so if you're interested in these slides here, I would update this before releasing it to you, okay? Okay, so let's go to the background, and we start with the definition of an electromagnetic waves. Everybody recognizes this, right? We just have to remind ourselves that an electromagnetic wave is an oscillating electric and magnetic fields perpendicular in time and space. So we have here the expression for the electric field, right? And you can see that k is the wave vector associated to the space propagation, and omega is the angular frequency which is associated with the time oscillation, right? The oscillation in time. Another important parameters, of course, is the wavelength and the period of oscillation, and associated to the waves, you have an energy which is inversely proportional to the wavelength. Right? So now you remember all this, we can move on. This is a scheme of the electromagnetic spectrum here, and we have an association of frequencies with familiar objects here in our world, right? So when we talk about optical properties of glasses, we're going to be focusing on the visible spectral range, infrared and ultraviolet. So we're talking of frequencies 10 to the minus 5, 10 to the 12 to 10 to the 16th hertz. Properties of light that are relevant for what we're going to discuss: the wavelength, of course, the frequency, the intensity, the polarization, and the phase. So when light interacts with matter, and again, remember when I say light, I'm talking about infrared to ultraviolet, right? This is what we call light. Usually what's perceived by our eyes, not deep UV though. So when light interacts with matter, there is an oscillation of the charges in the materials, right? So the electric field of light will polarize the charged species in the materials. The charged species can be dipoles or ions or electrons as you wish. The polarization will depend on the light frequency, the mass of the charged species, and also the bond strength between the species that are oscillating. And the interactions, of course, will take time and consume energy, which implies a reduction of the speed of light propagation. And then we come to refractive index. Refractive index is a super important, perhaps the most important canonical property of optical materials. So the refractive index is a measure of the speed that light of different wavelengths has in a certain media with the electric constant epsilon, right? So N, refractive index, is related to the dielectric constant and also the magnetic permeability here. So electric permittivity, magnetic permeability. But since for non-ferromagnetic materials, mu is practically 1, then we can assume that N will be proportional to epsilon r, which is the dielectric constant, right? And the dielectric constant, of course, is a complex number. It can be written as this, with a real and an imaginary part, right? And here we have a plot of the real and imaginary part as a function of frequency. So you just have to keep in mind that, again, dielectric constant, perhaps you could give a little help to Professor Ecker. Yeah, sorry about this. So then in the plot here, you can see that the imaginary part of the dielectric constant, which is proportional to the imaginary part of the refractive index, is what's responsible for the losses in the material, okay? So you can see in the plot here that you have some bands, right? And these bands, they correspond to absorption in different regions of the spectrum here, but it's not particular in these absorptions that we're interested, but rather on the dispersion, on the variation of refractive index in regions close to the absorption, okay? Because, why is this relevant? Because the dispersion of refractive index will have a lot of influence in these properties that I put here. So reflection, refraction, chromatic dispersion, and scattering. As you can see here, we pretty much can model and all these effects as a function of the refractive index of the material, right? So when light interacts with a transparent media, many things can happen. We can have reflection, absorption, scattering, emission, transmission. Huh? Good. So let's take a look into detail now of each one of these properties. And first one, of course, is reflection and refraction. So we have a scheme here. We have a material such as glass that is transparent, refractive index 1.5 in air, where the refractive index is 1, right? So we have a ray of light that incides here with an incidence angle θ1. And then, of course, we have reflection at the same angle. But part of the ray is also transmitted through the material if it's transparent in this wavelength, right? The thing is, because the refractive index is different in the glass, there will be refraction of this ray. So θ2 will be different than θ1. And this effect here is governed by the Snell's law, as you can see here. So the angle of reflection, reflection, is the same as the angle of incidence. But for refraction, you have a dependence with the change in refractive index. Okay, so we can model this, and this is very relevant, we're going to see later, because we need to correct aberration in lenses, by the Fresnel equations. The Fresnel equations assume homogeneous isotropic media and allow us to come up with a modeling for reflectance and transmittance as a function of the refractive index. So here, basically what you have is the power of reflection for S and P polarization Why is that relevant? S and P polarizations, because the Fresnel equations is based on the ratio of the electric field of reflected and transmitted light with respect to the electromagnetic field that is incident of a plane wave for polarizations S and P. So if you look at this figure here, you can understand what I mean. This is your sample, and this is a plane of incidence here. S polarized light will be perpendicular to the plane of incidence, and P polarized light will be contained on the plane, right? So then we can model the reflection power for S and P polarizations, and it's not so important to look at all the terms of the equation, but what I want you to notice is the dependence with the refractive index of the two media. And of course, because there must be conservation of energy, you have that the transmittance power for S and P polarization will be 1 minus the reflected power. We have some special cases to look at here. One of them is light propagation from medium 1 to 2 when N1 is smaller than N2, right? So air to glass, for example. If we do normal incidence, that means theta I equals 0. So normal incidence, that means that most of the light will be transmitted, okay? And only 4% will be reflected, as you can see here, for a refractive index of 1.5 of the material. Of course, this will depend on the refractive index, but most of the light will be transmitted, both in S and P polarization, as you can see in this graphic here, right? So angle 0, maximum TP and TS, and minimum RS and RP. There's another case here when the theta incidence is such that the RP component is equals to 0. So the P wave is refracted and the S wave is only reflected. And for a refractive index of 1.5, the Brewster angle is about 56 degrees. You can see it here, right? So you can see that RP, the reflection of P-polarized light, is 0, whereas RS is different than 0. So if you do incidence at Brewster angle, you have an opportunity to select polarization, right? And this is very much used in optical components, of course. And then you have the correspondence here of TS and TP. And if you have incidence at 45 degrees, what happens is that the reflected S polarized component will be squared with respect to RP. Another special case is light propagation from medium 2 to 1 now, with N1 smaller than N2. So now, the light ray is inside the media with higher refractive index, as you can see here. And the first case here is normal incidence, right? So we have, again, transmittance. Just a little bit is reflected back. But then if you change the angle of incidence, theta 1 here, you're going to start seeing refracted rays, right? And then I change the angle a little more, and then the refracted angle changes again, and so on, until I reach an angle of incidence here that I actually don't have a refracted ray anymore, but I have total reflection, okay? And this particular angle is called the critical angle for total internal refraction. So for angles higher than that, I will have rays that are 90 degrees to the surface, to the incidence. Sorry. For rays higher than that, I will have refracted light inside medium 2, which has the higher refractive index. So you can look here that at a particular angle here, TP and TS will drop to 0, whereas RS and RP, the reflected components, will be maximum because of total internal reflection. Is that relevant? Super, right? Because total internal reflection is the fundamental basis of the operations of optical fibers. So just out of curiosity, optical fibers is a market of $2 billion expected by the year 2030. Already in the 1840s, Colladon Babinet demonstrated the possibility of light guiding. In the 1850s, Tyndall showed experimentally the total internal reflection. In 1965, Cow and Hockham proposed that light guiding could be used in telecommunications. And this proposition actually granted Cow a Nobel Prize in Physics in 2009, many years later. But it was only in 1970 that researchers from Corning actually developed the first fiber optic. And this fiber optic at the time had a loss of 20 decibels per kilometer. Professor Marcelo will tell you more about that, what are the relevant aspects of the losses of fiber optics, but I can already tell you that the modern fibers now have losses lower than, much lower actually than 1 decibel per kilometer. Of course, you have different regions of the spectrum here where the loss varies, right? But we're basically talking about silica fibers with very low losses. So I was telling you that the variation of the refractive index is an important parameter because it has to do with chromatic dispersion. So the fact that the speed of light is different through a dense media, depending on the wavelength of this light, will cause a dispersion of colors. So if you have white light going through a prism, this is not new for any one of you, you have seen this, right? You're going to have a dispersion here into different colors that propagate in different refracted angles. And one way to characterize and to model this is through the Cauchy's formula here. This was the first approach. So away from the absorption peak, where I showed you the dispersion there and the electronic, ionic, dipolar absorption there, we have a dispersion of n, which can be modeled by this equation here, where A, B, and C are constants and can be determined experimentally. What's important here is that you look into this graphic here. We have for the BK7 glass, that's a crown glass from Schott. We have here in the visible region a very good agreement of measured results with the Cauchy formula that models the refractive index dispersion in the visible region, right? But you can see that in the UV and also in the infrared here, the matching is not so good anymore. So then there was a further developed that by Selmayr. So we have the Selmayr's equation here that shows the dependence now of n squared to lambda. And you can see now that we have a much better agreement with the green light and the measured results here of refractive index, right? So you can actually model this and you can measure the refractive index and compare with theory. Chromatic dispersions, of course, is favorable for wavelength analysis in spectroscopy, but it's unfavorable because it causes chromatic aberration in lenses. So imagine that white light is passing through this lens here. Because each wavelength will feel a different speed, it will be retarded, right? So then you're going to have a focusing of the ray, which separates the colors, as you can see here. So you're going to have this different circles with different colors, and of course you don't want that. That is called chromatic aberration. Is there a way to correct this? Absolutely. And this is the guy here who made the substantial contribution for the correction of chromatic aberration, Ernst Abbe. He was one of the persons working on the foundation of the Schott lab in Jena. I'm going to tell you a little more about that. So Abbe came up with a model here, which is known now as the Abbe number, that can relate now this number with the refractive index at three particular lines here, which are the Fraunhofer lines called D, F, and C. You can see the wavelengths here, right? So one of the ways to correct chromatic aberration is to combine lenses with different refractive index so that you can match the focusing of different wavelengths at the same focal point here. But there is a smarter way to do this, which is to develop lenses where you have a gradient of refractive index. So this is the great contribution of Ernst Abbe. More generally, for non-visible light ranges, because this equation only applies to the visible here, as you can see, you have this number here, the so-called V number, which can be plotted as a function of refractive index when you want to develop an achromatic lens. And this is, of course, super important for industry, for the many applications we have. So here you have a diagram that is called the Abbe vial of refractive index variation at a particular wavelength as a function of the Abbe number. So remember I told you that this number here allows us to choose the best glass to make the lens we want to make for a particular application. And we have a distribution here of crown glasses and flint glasses. Sorry about the vidro here, but I think by this time everybody knows that vidro is glass in Portuguese, right? So the crown glass is marked by K here. You can see all this region here is of crown glasses. They are silicates containing sodium, calcium, with low refractive index and low dispersion. Low dispersion means V number lower than 50. And then you have the flint glass, which are glasses containing lead with high refractive index and high dispersion with V higher than 50, right? So this was actually one of the contributions of Schott, that he did very systematic work with many special glasses to be able to characterize refractive index. Another important property here is, of course, scattering. Scattering is what will determine if a reflection is nice like that, what we call specular, mirror-like, or if it's diffuse like that. Both of these situations are also familiar to you, right? So scattering in general depends on the size of the scattering center. And we start by talking of elastic scattering, which we call Rayleigh scattering. That happens when the particles that are scattering centers are lower than lambda over 4p. So very small particles will show Rayleigh elastic scattering. No energy is lost. Again, we have an expression here, and we have the ratio of scattered light as a function of the incident light here. And what's most important that you perceive is that the dependence here is proportional to the inverse of lambda to the fourth power. That means that smaller wavelengths will be more scattered than higher wavelengths, right? So we're talking about blue light. UV and blue light will be more scattered by small particles than red light. And this is what causes, of course, the blue sky we have, right? So our perception of a blue sky when the sun is high in the horizon, right, is because of the primary scattering of the blue component of visible light. However, when the sun is coming down to the horizon, then the angle of incidence changes, right? And then you start having heavier, larger particles, for example, pollution, and then they start also scattering in other areas of the spectrum. That's why you see this reddish yellow color of the sky. And of course, I'm talking here about scattering centers, I'm focusing on particles, but when we talk about glasses, I mean density fluctuation. So that basically means that in some areas of the glass, you have refractive indexes that are quite different, right? Not quite, but slightly. Enough, though, to show Rayleigh scattering. And this is the coefficient here that takes into account scattering. And again, you can see that it's dependent on n squared. And here we have kappa, the isothermal compressibility, the Boltzmann constant, and the fictive temperature of the glass. Scattering can also be used to our favor For example, in these beautiful applications here, do you know what this is? Do you know what the color here is made of? Any idea? You probably have seen the Lycurgus cup, right? It's a very famous art piece, very ancient, available at the British Museum. And it's very interesting because in reflected light, it's green. But if you put the light source in the back, you're going to see red color in transmitted light. How come? Any idea what causes the coloring here? That's a scattering. By what? Tiny transition elements, actually metals. Gold and silver nanoparticles that are added to the glass composition here and will contribute to the scattering of light. Very tiny little particles, colloidal suspension added to the glass synthesis, right? And also here, the ruby glass. This is a very famous glass prepared by Johannes Kunkel, 17th century. And you also have a distribution here of colloidal gold nanoparticles. Of course, in this particular glasses here, I have to tell you the whole story, because it's not only scattering, there's also absorption, right? So you cannot dissociate both phenomena because you have a dispersion of the particle size, okay? So remember that scattering will depend on the size of the particles, and this is very hard to control in metallic nanoparticles. Now that we talked about Rayleigh elastic scattering, we go to inelastic Raman and Brillouin scattering. And inelastic means that there is some loss of energy, or there is some change of energy, right? Because we'll see that for Raman, we can actually also have a little bit of a gain of energy. So basically, a change of polarizability should occur during vibration that will cause the scattering here. And so you have the Rayleigh scattering, you have the incident light here coming out of the sample with the same energy that it entered, right? I want to make it very clear, I'm not talking about absorption, okay? There is no absorption. This is just interaction of light with matter that will cause a change of polarizability of the atomic species that compose the matter, right? So here we have Rayleigh scattering. However, there could be that the sample absorbs a little bit of this energy that was incident, and now I'm going to have light coming out with lower energy. And it could also be that the light coming out has a slightly higher energy. These two cases here are called Stokes and anti-Stokes scattering, okay? So basically, photons are scattered by effect of vibration and rotational transitions, and that involves the changes in polarizability and characterizes the composition of matter. This is what we call Raman spectroscopy. So this guy here was the first one to demonstrate Raman phenomena experimentally, although it was already predicted many years before. And for Brillouin scattering, we have a similar situation, except that now we're talking about acoustic phonons. So the phonon scattering now is done by large-scale, low-frequency phonons. And this characterizes the elastic behavior of matter. Both informations are important, of course. So just to give you an idea of the difference here, we have the optical phonons, which are related to atomic vibrations and changes in polarizability, right? And the acoustic phonons is as if a whole wave of atomic oscillation happens through the material, right? So we're talking about wavelengths that are much smaller here, higher energy propagation. So Raman spectrum, of course, is very useful for the characterization of materials, in particular glasses, because it gives you a fingerprint of the sample. And here we have a very simple schematic representation of the change in polarizability. If we consider a heteronuclear diatomic molecules in the presence of an electric field, you have an induced moment here, which is the product of alpha and epsilon, where epsilon is the electric field and alpha is the polarizability, right? I'm sure that Rafaela where is Rafaela? Gave you a full explanation of that, so we're going to go fast here. But basically, I have, again, the expression for the electric field, and then I have the expression for polarizability, which oscillates around an equilibrium position, right? And if we multiply now alpha and epsilon, as in this equation, then we come up with the expression for the induced moment here, right? And the expression, when you solve the mathematics here, gives you this very interesting contribution of Rayleigh scattering with Ni, anti-Stokes, Ni plus N0, and Ni minus N0 Stokes. So all the contributions of elastic and inelastic scattering. Here's a very didactic example here, although it's not in a glass, it's in CCl4. You can see the Rayleigh line very intense, okay? And this, of course, will be the primary scattering. This is 99.9% of the scattering. And then you have the Stokes component here at lower energy, and you have the anti-Stokes at slightly higher component. This one here is rarely, I shouldn't say rarely, but it's very difficult to detect because the probability of happening is much, much smaller than this one here, right? This one is about 1%, maybe this is 0.1%. But of course, what we are interested in measuring when we want to characterize the vibrational structure of the glass are the Stokes line here, because they are detectable, and this difference in frequency here from the Rayleigh to the Stokes line will give me the vibrational energies of the glass, as you can see here, right? And then we often talk about phonon energy, and we say the maximum phonon energy, the maximum vibrational energy of the glass is, I don't know, 1,000 centimeter minus 1. And this gives you an idea if this is a good optical glass or not, because the vibrational component will affect the radiative probability. Okay, so we talked about Rayleigh scattering for particles that are very small, much smaller than the wavelength. Now we talk about Mie scattering, and that applies for particles with R at the same order or higher than lambda, okay? So now IS over I0 is proportional to lambda, and some examples of Mie scattering you can see, for example, in the opaline glass. It's a glass that contains sodium phosphates, NaCl, calcium phosphates, and other additives here. And Mie scattering is usually characterized by this milky appearance of the medium, right? Just like when you put a little bit of milk in a glass of water, you can see that this milky appearance will cause scattering of light. So you can actually do artistic work. You can see some beautiful pieces based on Mie scattering here by addition of particles. And this is what also explains the blue color of some eyes, right? Because the eyes have some structures in the iris that will scatter blue light rather than being absorbed. Like I have brown eyes because I have too much melanin, right? So blue eyes have very little melanin, they absorb little, and therefore the scattering is much more visible, and that's why you see this blue or sometimes even yellowish green tinges, right? Depending on the wavelength that is scattered. And that's also responsible for the blue light that you see of cigarettes against a black background, right? Because again, the blue is more scattered. And one thing that is good to know is that Rayleigh scattering and Mie scattering, they have different dispersions of the scattered light here. So in the case of Mie scattering, there is a preferential direction of the scattered light. This can be relevant for applications as well. So scattering is super important because it affects transmittance, of course. Transmittance is measured as a percentage here, the ratio between I and I0. And transmission through a homogeneous glass as a function of frequency depends on basically three factors: scattering, electronic absorption, and vibrational absorption, okay? When it comes to electronic absorptions, we have band-to-band transitions. Then we have the Urbach edge transitions here, number 2. We have absorption by defects in the middle of the gap, such as a dopant ion, and we have absorption by free carriers, as it's shown here for the conduction band. Vibrational absorption will characterize the vibrational modes of the bonds, as we already mentioned. But remember, I was talking about scattering and vibration, and now I'm talking about absorption and vibration, right? So we can also have absorption of frequencies by vibrational modes of the sample. Extrinsic factors that add to this attenuation are impurities, dopants, heterogeneities, defects, etc. So now we go to absorption, and then we're gonna look at absorption in different regions of the spectrum, okay? We start by UV. So we're talking about high energy. Most glasses are opaque in the UV due to strong electron excitation. So this means that an electron goes from the valence band to the conduction band, right? And this characterizes the UV cutoff, where the glass or the sample starts absorbing in the UV. Two effects here: intrinsic excitation of electrons from valence to conduction band, as I just said. In order for that to happen, the energy of the photon must be similar to the energy of the gap. And number 2, electron charge transfer between ions, which can be major or minor constituents of the glass. For example, when you have a redox reaction. More precisely, it's better to use, instead of using EG, that we often call gap energy for semiconductors, is to use this E0 here, which is the mobility gap between the mobility edges of the valence and the conduction band, okay? So that's why I wrote this particular equation here that characterizes the absorption coefficient as a function of frequency for different mobility gaps, E0, okay? So if we look at this graphic here, this graphic plots this absorption coefficient as a function of photon energy. And we have different semiconductors here. You can see that E0, of course, will change. It can be, by this equation here, you can see that it can be obtained by extrapolation of the linear parts of these curves. So, but this is an extrapolation, because if you look, there's always a tailing here for energies that are smaller than E0. You can see here, okay? So these particular tails, they are called Urbach edge. So this region here is better characterized by this expression for the absorption coefficient here. So this is absorption at the very edge of the conduction band, right? And you can see for some chalcogenide glasses here how much we have a change of the absorption coefficient as a function of the photon energy. So this is absorption in the UV, right? I was talking about intrinsic excitation of electrons, and regarding charge transfer, as I said, if you have any impurities such as iron, you can have redox reactions which involve transfer of electrons. And this can also happen with the constituents of the glasses, as Professor Helmut Eckert showed in his talk when he was talking about the photosensitive glasses, right? That you have all these redox equations, reactions happening. Now we look at absorption in the infrared. So we go from ultraviolet to near infrared. Now this is the region I'm talking about. And now the phenomenon involved here is a change of electric dipole moment, okay? So this is the dipole moment. It's a product of distance and the charge. And a change of mu must occur during vibration so that you have absorption in the vibrational area. Why does that happen? Because we have vibrational modes associated with all these atoms here that are in the first coordination sphere, right? So you have here the fundamental vibration modes for an XY4 molecule like silicon oxide. And then to model this, we start very simple with two atoms here connected by a bond that has a force constant K, right? So we usually use this classic approximation to start describing the system. So this can be modeled by the harmonic oscillator model. And then if we solve for the energies, we can get here the vibrational energies associated with the system. And then each one of these vibrational energies will characterize a certain mode of vibration. And one thing that is important to mention here is that FTIR, the technique that allows us to measure vibrational absorption, is complemented by Raman. Because remember, we're talking about different phenomena. So one is change of polarizability, the other one is change of electric dipole moment. So for a diatomic heteronuclear molecule, this bond strength is proportional to the constant force of the string that connects these two atoms, right? And if we solve these equations, if we solve the harmonic oscillator Hamiltonian here, applied to the Schrödinger equation, you come up with the values of energy, and this is the natural vibrational energy that will depend on the force constant, that's the strength of the bond, and mu, and the harmonic vibrations here will happen between states with delta V plus minus 1. However, when we go to a polyatomic molecule system, then the things get a little more complicated, right? Because we don't have just one vibration, as in this case, but now we have 3n minus 6 normal vibration modes considering n atoms, right? So now I have the vibrational energy being described by a sum of different energies corresponding to different transitions here of all the vibrational modes in a particular vibrational state, okay? And of course, when you go to solid state, like in a glass, then the situation is even more complicated because then the vibrations are not harmonic anymore. You have unharmonicity, combinations of frequencies, and then the selection rule, delta V plus minus 1, is relaxed. You can have overtones and combinations of bonds. We're not going to go into these details because we don't have time, but what I can tell you is that by characterizing the absorption in the infrared, you can have a good idea of what's the best glass for your optical application. So this is the curve here for the Pyrex glass developed by Corning. Everybody has heard about Pyrex, right? It's used for kitchenware, basically. Also has some specific applications. It's a borosilicate glasses invented in 1915. And here we have the relative transmittance for different glasses like silica glasses. Ziblan is a fluoride glasses, sulfide, selenide, telluride, chalcogenide glasses. Right? So you can see that you can get pretty extensive transmission, but of course the intensity will drop in the infrared. Here we have an example. This is one of our works here of phosphate glasses, sodium aluminum phosphate glasses containing ytterbium and thulium. And this is the transmission window in the infrared. We prepared these glasses in air, atmosphere, and in nitrogen. You can see a big difference here of the transmission window because in this particular region, water, OH vibrations absorb a lot. So these are definitely glasses that you have to prepare in controlled atmosphere if you want to guarantee that you're going to have extensive transmission in the infrared. And this is actually a ceramic here that it was sintered. This was part of my PhD work, so a long time ago. I was working on PLZT, hot press, the transparent ceramics. And we were able here to measure the whole optical window, the transmittance from the UV to the infrared here, as you can see. And this particular sample, which was the best one I could obtain, was about 70% transmittance 2.5 millimeter sample with this very good transmission window. Okay, so we talked about UV absorption, infrared absorption. Now I go to absorption and emission in the visible and near infrared. And here the transitions can be described in the framework of molecular orbital theory or ligand field theory, depending on if you're working with molecules or ions, right? So absorption in the visible can be of three types. Can be electronic transitions between orbitals of transition elements, or transitions across the band gap, as we already discussed in the Urbach edge, and plasmon resonance of metallic nanostructures. You remember I mentioned when I showed you the cups that had colloidal gold particles. And here I deliberately chose the case of rare earth ions. Rare earth ions are those in the series of lanthanum to lutetium, plus scandium and yttrium, which are not in that particular series, but they are very similar chemically. That's why they are included under the rare earth category. And these particular ions, why did I choose them? Because in the trivalent state, they are the most important for technological applications these days. So I would like to tell you a little bit about them. They present 4F transitions through a mechanism that we call forced electric dipole. We're going to understand that a little better soon. So what are the characteristics of the rare earth ions here? We have a distribution here of the electronic levels as a function of different influences, right? For example, Coulombic interactions will cause some breaking of the degeneracy of energy levels. Then you have very strong spin orbit coupling in these ions because they are quite heavy, right? So then you have the effect of spin orbit coupling, and then you have crystal field splitting. You can see that this effect is minor as compared to spin orbit, and then you have magnetic field splitting, which can give rise to the EPR transitions that Professor Eckert explained. Another interesting thing about these trivalent ions is that the 4F active, optically active orbital here is internal to 5s and 5p, where the bonding actually occurs. This means that the electric field caused by the ligands around the atom influence very little the energy structure of the levels, okay? Because the transitions happen internally in 4F orbitals. And this is a distribution of the radial probability of the orbitals here. And you can see that 4F is more internal, whereas 5s, 5p, 6s are more external. So this is important to keep in mind. The rare earth ions do not feel so much the influence of the ligand field as the D metals, for example. Everybody probably has seen spectra of copper, cobalt, or whatever, where you can see large difference in the absorption and emission spectra because of the influence of the ligand field, right? If the field is stronger or not, you're going to see different bands. Not the case here. So these transitions, they are quite characteristic. They do not change so much in wavelength, and you have a huge selection of transitions to choose from the visible to the infrared. A very important transition here that everybody should know about is this one of erbium at 1.5 micrometers, 1500 nanometers, which serves what purpose? Do you know? Why is this transition important? What happens here in this particular wavelength? Telecommunications, the transmission of optical signs in telecommunications. Okay, so this is the first window here of transmission. Of course, there are others that are used these days, but this is the first one. Okay? And then you have other transitions of neodymium, ytterbium, holmium, thulium. These are the most important active rare earth ions. Some of the applications are listed here, as you yourself can read. And these photographs here were taken from glasses developed in my lab by some of those guys sitting there. For example, Tiago, Whom else is there that prepared the glasses? Valdinei, do we have any sample from you here? No, I think only from Tiago. Good. So, rare earth transitions can be treated by perturbational theory. Okay? So very briefly, we're not going to go into too much details, but this is the quantum mechanical description, and we start, of course, with a simplified two-level systems here. Okay, state M and state N. Then there's a photon that comes here, and if the photon is in resonance, there will be a transition, right? So the Hamiltonian that describes the system here, H, is the H0, which takes into account for the unperturbed system, plus H1, which is time-dependent and is given by the photon that is interacting with matter now, right? So for an electronic perturbation, we have that H1 is the product of the electric dipole of the sample times the electric field of the photon that is interacting with, right? So we can now write this. Okay, so this is the electric dipole here, and this is the electric field, as we wrote before. And then I can use this particular Hamiltonian with the perturbation contribution to solve the Schrödinger equation, right? So you must be familiar with this. When you solve this, of course, I gave a huge jump here. You can get the eigenfunctions and the eigenstates. And then by solving these mathematical steps here, it's not important that we go through this, right? We will end up with this so-called coefficients of weight. And this AN here, they basically characterize the weight of participation of different levels in a certain transition, okay? I know that sounds a little vague now, but you will understand the importance of determining this variation here of the coefficients of weight. So it basically describes the contribution of different states for a certain transition between two different states. What's more important here, as I said, is that this variation, if you take the model of this and square it, this will be exactly what you are looking for, which is the transition probability, right? And the transition probability, now you can understand this better, is due to the square here of this integral, which connects state M and state N by the perturbational Hamiltonian H1. Okay? Does that make sense? So the two states will be connected by H1, which is the perturbation given by the photon that incides on the sample. That's the transition probability. Now, the transition probability can also be rewritten as I did here. So now you have the states here that I call Cm and Cn, right? And this is H1. So it's the product of mu and epsilon. And a transition will only be allowed if this particular integral here is different than 0. That makes sense, right? So this integral must be different than 0. And since the electric dipole operator is an odd function, then the states M and N must have different parities. Why is this relevant, right? Saying that states have different parities mean that they have to be from different orbital states, right? So I can have, it's very common to have a PD transition or a DF transition, but not an FF. Because when I multiply these parities, F and F have the same parity. But then the electric dipole operator here has odd parity. Then when you multiply an odd function by an even function, that will give 0, right? So you have to make sure that this integral is different than 0. And because of this, there are some selection rules that must be obeyed for the transition to happen. And one of these selection rules is the parity rule, which says that delta L must be plus minus 1. Okay? So you can have a transition P to D or D to F, but not F to F. And now I got you confused, because in the previous slides I said that the transitions of rare earths are 4F, 4F. So how can that happen? Huh? Furthermore, to secure spin angular momentum conservation, we also have another rule. I'm sorry about the deconfiguration here. We have another selection rule that says that delta S must be 0. So the spin from one state of the electron in one state must be the same as the spin on another state after the transition is done, right? An inversion of spin is not possible. That's the selection rule of spin. And because J equals L plus S, then we have that delta J must be 0 plus minus 1. Okay, so now you must be wondering, how come FF transitions happen in rare earth ions? Because in this case, delta L equals 0, and sometimes delta L, I don't know what I meant here. Delta L equals 0 here. So let's take a practical example. We have neodymium here, and this is the distribution of electronic levels. It has a characteristic absorption at 800 nanometers, and this very important emission at 1.06 micrometers, okay? This is the most important emission of neodymium ions. Have you heard about neodymium YAG laser? Probably, no? So this is where the YAG laser shows its main emission here, 1,000 micrometers. So when we look at the spectroscopic term here, what can we conclude? The transition is this one. This is the state where it starts, and this is the ground state of neodymium. First thing, that delta L equals 0. So we are violating the parity rule. Second thing is that delta S equals 0 because S is given by this here. So good, we are obeying the spin rule. Delta J equals 4. So again, we are violating the J rule, right? So how come the transition happens and is so important technologically? It happens because the ligand field here, I told you, it does not influence too much the electronic levels, but it influences enough to perturb the system so that the parity of the wave functions is not so well defined. So it's actually the odd part of the electric field here, of the ligand field, that will perturb the wave functions F, and then the symmetry will be broken. Once the symmetry will be broken, there will be some even parity, and then we say that the selection rule is relaxed. Okay? So now we can have delta L equals 0. Now let's look at another transition of neodymium. This one is in the blue here at 480 nanometers. This one has delta L 0, delta S 1, so again violating the spin rule, and delta J equals 4. And now you ask yourself, what is the reason why the spin rule is relaxed in this case? The reason being there's a strong spin orbit coupling. So when there is a strong interaction between spin and angular momentum, then these numbers are not good anymore. They're not pure, they're mixed, and then you have selection rule relaxation. Okay, I'm not going to bother you too much with the theory, but let's take a look at some practical examples of absorption and emission in the visible to near infrared in erbium-doped glasses. So these are also glasses that were developed in the lab. You can see here the absorption coefficient is characterized here by the ratio of light that went through the sample and light that was incident on the sample, right? By the so-called absorption coefficient, and this, of course, will depend on X, the sample thickness. So this here is a particular fluorophosphate glass doped with erbium that shows very promising characteristics as a laser-active media. You can see the characteristic absorption lines of erbium, and what you see here is the Urbach edge UV absorption that I showed you before, right? So it's the absorption of the glass matrix itself. And you can see that as I increase the erbium concentration from 0.1 to 5 mol%, I have linear dependence of the absorption coefficient. This is not always the case, of course, because sometimes you start having clustering of the dopants when you increase the concentration too much, right? Then you don't have this linear dependence anymore. You start having kind of a plateau of the absorption. And here we have emission. Remember I told you that 1.55 micrometers is this very important wavelength for telecommunication transmission, right? So you can see here the emission as a function of dopant concentration. And this is quite interesting because you can see if you increase from 0.25 to 3 mole percent, we have an increase of the emission. But when I add 5%, then the emission decreases. Do you have any idea why that happens? If I increase even more, 10% erbium doping, the emission will be even lower. Would you like to give me some examples of why this should be the case? Yeah, glasses. The dopants, right? Yeah, and when you have clustering or approximation of the dopants, what happens? What happens? The math people, come on. Huh? They start interacting and exchanging energy, right? How? Non-radiatively, right? So when you start having a large number of dopants, they start getting too close, and then some dipolar interactions will also lead to non-radiative relaxation. Okay. Good. And this is very well characterized by excited state lifetimes here. You can see that for lower concentrations, you have a longer lifetime. So the lifetime is the time that it takes for the excited level to decrease by about 1/3 of its initial population, right? So when you characterize this lifetime here, this is something you can measure, then you will see that as the dopant concentration increases, then the ions start pairing, they interact, they exchange energy, so you have different channels of deactivation, and the lifetime will drop. So these are some important parameters I would like to show you here. One is the radiative transition probability, of course. You can see here the integral to the square that connects the states A and B, right? By perturbation here associated with the electric field of light, right? The radiative lifetime values will be the reciprocal of the transition probability, so tau equals 1/A. And the quantum efficiency is defined by eta, that is the experimental lifetime value divided by the radiative value. This only means to say number of photons that are emitted by the number of photons that were absorbed, okay? And you might think that this energy transfer between the ions that I mentioned that cause non-radiative decay, you might think that this is always something to be avoided, right? So we must find the right concentration to optimize the radiative transition probability, but sometimes energy transfer can be used in our favor. For example, in the case of thulium. So let's try to follow this here. We have an excitation in the red, 650 nanometers, and then we have an emission here at 800 nanometers, okay? However, this state here is a metastable level with quite long lifetime. And then what happens is that it serves as a reservoir of population. So if there is another thulium ion very close to this one, what might happen is that there is non-radiative decay of this particular ion by interaction with this close neighbor. So then this energy here, lost by heat, will be absorbed by the close-by ion, which will be promoted here. So now I started with 1 electron here and several electrons here, but I end up now with 2 electrons in this particular state. And if this happens very efficiently, this is called cross-relaxation, then I'm going to have an increase in this particular emission at 1.8 micrometers. This is a super important emission because it's used in lasers for cosmetic treatment. Why is that? Because 1.8 micrometers is a region where the skin absorbs very superficially, so you can use this laser, for example, to get rid of your wrinkles, right? So you have these pulses at 1.8 micrometer of thulium that will happen to blow the cells that form your wrinkles. Okay. So, anyways, this is exactly what I'm saying here. So you have thulium doped with 0.1 mole percent and 6 mole percent. When you have low concentration, the emission at 800 nanometers is more intense than the one at 1.8. But once you increase the dopant concentration, then this one here is much less intense. And this one grows, right? So the intensity here is much higher because of the cross-relaxation energy transfer process. Radiative transition probability is favored by high refractive index, but you have to be careful, because if you're trying to make a laser-active media, if you have too high refractive index, then it's hard to focus the light, because you're going to have too much refracted contribution, right? It's unfavored by high phonon energy. It's unfavored by heating and ion-ion energy transfer in some cases. As I said, energy transfer can be used to one's advantage. This is another example. Now we're talking about erbium. Erbium shows a very interesting property, which is it absorbs here in the infrared. And again, because this is a metastable level, sorry, this is erbium, okay? Let's focus here first. So erbium absorbs at 980 nanometers, that's infrared. And then there is some relaxation that populates this intermediate level here. And then, because this is a metastable, long-lived level, there can be excited state absorptions. So another photon comes with the same wavelength and is absorbed from here now, or even from here. And this means that I get upper states populated, and then I can also observe emission in the green and red. This phenomenon is called upconversion. Have you heard about it? Yeah? Right? Upconversion. It's also a very important process that finds many technological applications. For example, have you seen these glasses for these military glasses that you see thermal images in green? That's upconversion. Basically, what the glass does is to capture infrared light, convert it to high energy, and then the emission is in the green. That's why your vision is green, right? So that's exactly a good example for upconversion used in defense. Now, here in this diagram, we have something else. There's another ion here, ytterbium, which is often used as a so-called sensitizer. So basically what happens is that it also absorbs at 980 with a much higher absorption coefficient than erbium. So what we often do is to combine these dopants so that this one here will help to harvest the infrared light and transfer to erbium. So ytterbium can also be used with other ions to improve the emissions. Now look at something interesting here. I told you you can see emission in the green, right? Actually, from two levels, these two here that are very close in energy. They are so close in energy that this difference here can be coupled by thermal excitation. So if I heat up my sample, the electrons that are in the lower state will populate the upper state, okay? And you don't need so much for that because this energy difference is small here. It's of the order of the Boltzmann distribution. So basically, if you do a spectrum at 40 degrees Celsius or at room temperature, you can see that there is a difference in intensity of these two green emissions, right? But as you increase the temperature, to 160 Celsius, you can actually see that there is a change in relative intensity, okay? So normally when you have two excited states, the one with lower energy will be more populated. That's Boltzmann distribution, right? However, if you interfere, if you heat up the system, then this one will also be more populated. So the emissions from here and from here will vary in intensity. Why is this relevant? Because now we can use this intensity variation of the two bands to construct an optical thermometer. And this is a super important area of research nowadays. There are many people looking into better optical thermometry. The nice thing about this is that you can do measurements of temperature remotely just by using a laser. You don't actually have to go there and touch. So for example, if you have electrical leakage in, let's say, in a transformer, in a high tension transformer on a lamp post or something, right? How do you measure, how do you know that there is electrical leakage, right? One of the ways is by measuring temperature. So you could install a sensor like this, and then you can measure remotely the temperature difference. Am I okay in time? Almost finishing. Yeah? Good. Or not? How much? 15 minutes. Okay, that's good. Yeah, okay. So anyways, this is some work carried out in the lab also. Now it goes very fast. Ooh, sorry, it's all mixed up here. But besides fluorescence, we also have some other properties of glasses and glass ceramics that I didn't mention before that are super relevant in dentistry, for example. I believe that tomorrow when Oscar Paito talks about bio-glasses and bioceramics, he will tell you a little bit about dental glass ceramics. And so we have some properties such as opalescence, translucency, gloss. You know, they have to do with scattering, absorption, fluorescence. So all of this must be looked into if you want to have a restoration that looks closer as possible to your natural tooth, right? So there's a lot to talk about that, but we're not going to go into this. And of course, you can tailor these properties by appropriate dopants of the glass ceramics, of the glass composites. So this is what some researchers are doing also, focusing on betterment of these resins. Good. Very quickly now, just a tour through the techniques for the characterization of optical properties. How do we measure refractive index? Very simple. Snell's law that I showed you before, right? And you use an equipment called a refractometer. This is a classical Abbe refractometer, and this is a more modern digital refractometer. The principle is the same. You have a source of light, you have a filter to choose the wavelength, then you have a lens focusing, and then you have a prism that is coupled to your sample. So there must be some coupling of the sample against the prism, okay? So you have two media here with different refractive index, your sample and the prism, and then you have a CCD sensor here where you will collect a total reflection. So when there is total reflection here at the angle that is total reflection, so if you know this angle and you know the refractive index of the prism, then you will be able to determine the refractive index of your sample. So it's very simple. UV-vis absorption spectroscopy is also relatively simple. Here are some descriptions of a spectral region, excitation source. The dispersive element can be diffraction gratings or interferometers, detectors. Samples can be bulk materials, films, or liquids, right? It's very simple. You have a broadband emission, like a lamp. Then you have an element of selection of wavelength, which can be diffraction gratings or interferometer. Then you have specific wavelengths coming through the sample with a thickness X, and then you analyze the light that comes off. So, For the absorption spectroscopy, we take into account the Lambert-Beer law. You remember? It connects here the ratio of I over I0 to the absorption coefficient and the thickness of the sample. And of course, you can also estimate percentage of transmittance from the determination of absorption. So these are some, just to show you here, this is a dispersive spectrometer. This is how it works here. You have a lamp, you have a monochromator to separate the wavelengths, then you have two beams, two I0 beams. One goes through a sample, the other one goes through a reference. So you can have, for instance, a glass that is doped with erbium, and the same glass undoped, okay? So then we're going to be able to measure just the contribution of erbium if it doesn't interfere with the structure of the glass, right? And then in the end here, you're going to measure the ratio of these two contributions. Okay, this is just a representation here of a diffraction grating. So you can have a diffraction grating with different numbers of lines that will allow separation of wavelengths, right? The higher the number of lines, the more you can separate the wavelengths. Of course, the intensity is a little lower, but you have experimental choices for that. This is a equipment that we actually have available in our lab here. It's a Perkin-Elmer spectrometer. It works exactly in this principle of dispersive elements that I mentioned to you. So you have here two sample holders. Can you see? In one of them, you put your sample, in the other one, the reference, okay, the blank. And then you can measure this relative absorption. And this is the configuration inside. Don't worry too much about that. But all I want to call attention here is that this is a very sophisticated combination of diffraction gratings to be able to get very high resolution, to separate light with very high resolution for incidence in the sample. You can also use an interferometer for that, right? Again, we don't have time to go into details, but interferometric spectrometers, they rely on the interference of some rays. So basically what this does here, it's a Michelson interferometer. It promotes the interference of some rays that can be negative or that we call interferogram, right? And of course, you cannot read this. If I give you this and say, okay, what are the absorption frequencies? You cannot read it because this is just a variation of intensity as a function of frequency. So what we have to do now is to use a mathematical tool, which is Fourier transformation, and then we find out that this actually corresponds to these three frequencies here. And this is done automatically by your equipment. So this is an example of a Nicolet FTIR 850 spectrometer here. This one is dedicated to vibrational spectroscopy, okay? The Perkin-Elmer I showed before is UVV, near infrared. This one here is mid-infrared for vibrational frequency measurements. It's a classical equipment. Again, this is the how it looks inside. And in this case, we don't have diffraction gratings, but we have an interferometer because we needed to have higher resolution. Or you can buy something very small like this. This is a Carey 630 spectrometer that also allows measurements of vibrational structure, and it's very compact. We have one of those in the lab. Photoluminescence can be measured using LEDs, lamps, or lasers, right? You choose your source depending on your need. You also need a monochromator to disperse the light, some locking amplifiers, and a computer. Here you have two options. You can mount, you can assemble your experiment with individual pieces, or you can spend something like $250,000 or more, depending on the accessories, and buy a spectrofluorimeter like this, which is the one we have in the lab. And this will allow you to measure emission, excitation, lifetimes, and steady state, time resolved, whatever you like to play with in glassy or other samples. This is just the scheme here, not so important to you. As I said, I'm not going to go too much into applications, but I just would like to show this slide just to give you a little bit of a taste of the history of optical glass applications. Of course, it started already in the 1300s with the development of glasses, the spectacle glasses. That's very early. And then 1609, the telescope by Galileo Galilei. This is what gave the first application, let's put it this way, that first caught the attention of the world to the importance of developing lenses based on glasses, right? And then some landmarks here, 1660, the flint type glass with PbO2, because there was a need to correct chromatic aberration, and so you needed refractive indexes that were higher. And 1800s, Fraunhofer, Faraday worked together to improve glass production. In 1884, there is a very special landmark here because the Technical Jena Glaswerk Technical Lab was founded in Germany by the chemist Otto Schott, Ernst Abbe, the physicist, and Carl Zeiss, who was an entrepreneur, right? You know these names, I'm sure. 1887, they developed borosilicate glasses. 68, the very famous zero-dur glass ceramic that composes telescope mirrors these days. So this very large telescope and the extremely large telescopes are based on Schott's zero-dur glass ceramic. 2013, they developed a ultra-thin glass, 25 micrometers, which impacts, of course, the industry of smartphones and tablets, because now you can fold your screens, right? And at the same time, you know, development was happening in the United States through Corning. So Corning was founded in 1851, and then you have several landmarks here. So for instance, fiber optics that I mentioned to you, optical fiber patent in 1955, laser glass 1961, photochromic glasses, waveguides, and so on. I'm sorry that I had to change the computer, so that's why you see this mess in the configuration. One very important development here also was 2006 when Corning came up with the so-called Gorilla Glass, which is probably the glass in your cell phone there. Okay, good. So this is more of the same. I am trying to motivate you to study optical properties, so that's why I keep talking a lot about the relevance here, but my colleague, Professor Marcelo, will dig into this. I would like to thank here my research group that, as I said, is still active in São Carlos, and my new group now at BAM. Some of them you recognize here. Dr. Ralph Miller, Christian is here, right? And Patrick, where are you? Right here, yeah? And so I would like to thank these people who work closely together with me. Of course, all the funding agencies and academic institutions involved in CERTEV, which is our glass center here. And thank you for your attention.
Thank you very much, Professor Andrea. We have time just for one question.
I'm sorry it took so long, but we also started late.
No, it's okay. People can ask during the conference. I have one question. Does the size of the nanoprecipitates affect the efficiency of emission in glass ceramics?
Definitely, because it will affect scattering, right? So this is definitely something you want to control.
Is there an optimum size?
That's hard to say, but it should be smaller than the wavelengths that you want to practice in your glass, right? So it depends a lot on the region of application, if it's infrared or if it's more to the visible blue, this will, so you have to make sure that the inhomogeneities are in very small scale, less than the wavelengths.
Okay, thank you. So thank you again, Professor Andrea.
Okay, so if I'm sorry, If you like to talk, because we don't have time now, you can approach me anytime, okay? Thank you.
Marcos, during coffee time. Okay. Okay, so Marcos is just reminding us to remove the posters during coffee break now. And let's start coming back at 10 o'clock to another lecture, okay? Thank you very much. Have a nice break.
André. Sorry.
Good morning, good morning. Few announcements. So the bus will leave, for those who are taking the tour to the farm, Santa Maria Farm, the bus will leave at 1:30 from the hotel. Good advice is some sunscreen in a hat, if you have one, because it will be really sunny. UV is like 11. It's the maximum possible UV level you can have today. No clouds, so a lot of UV. For those who registered to get postgraduate course credits, please sign this list. This is an extra list here. Course credits, this is an extra list here. And for all of you, there is the regular list of, attendance to be signed. So those who registered have 2 lists to sign. Well, one is here. One of the toughest tasks of a conference chair is to get people back from the coffee break. This is a very hard task. At all conference chairs face this problem. And I'm facing this problem again. But okay, we have 80% of the attendees here, so I think we can start. It's a great pleasure to introduce Professor Marcelo Nalim. He is a member of our CERTEV, our center, which includes 2 universities of São Carlos. But then he moved to Araraquara, which is a satellite city to São Carlos, 30 kilometers from here. So we still consider him to be a São Carlos person. Marcelo Nalim is an expert on optical glasses and optical properties of glasses. So following up Professor Andrea's talk, he'll continue on a similar subject, optical glasses and photonic materials. He is also a very important person at our sponsor, FAPESP. He has a very high seat at FAPESP. He works 1 day per week or so at FAPESP. So thank you very much for all this funding, Marcelo. This is not the reason why I invited you here, But, maybe 50% or so FAPESP, 50% because of your achievements. Thank you, Marcelo.
Hello. Okay. Thank you, Edgar. Thank you for this introduction. And it's a quite pleasure to be here today to talk with you and to talk a little bit about photonic glasses. My talk will be more specifically with applications, and I will try to talk a bit about several types of applications, different applications on photonic glasses. Something that we developed here, something we don't really develop here in Brazil, but most of them we are developing in our laboratory and of course, in cooperation with other groups here in Brazil and also in France and the United States and Canada. So it was really nice. The first talk from Andrea, she gave us all the formal background, thank you. The formal background on physics and all the properties that we are related. And so let's move here a little bit. Let's see if, okay. This is our group today in Araraquara. We have this two research groups. One is photonic materials group. The leader is Professor Sidney Ribeiro, and we have also LAVI groups. This is the group I'm the leader, and together with Silvia Santanelli and Douglas Franco, we are studying the optical glass in Araraquara. As Edgar told you, we are quite close from São Carlos. We are 35 kilometers far from here, in the middle of the state, here. And Araraquara, in fact, this is an Indian name. It means the house of the sun. So it's a little bit hotter than São Carlos. We are pretty close, but in average, we are 4 degrees hotter than the weather usually here in São Carlos, but it's quite a nice city. This is our campus. This is all. São Carlos is quite here a little bit, just here. Sorry. Yeah, it's not a good map, in fact. So this is our Institute of Chemistry in Araraquara. We belong to the university. This is, in fact, this map here. Unesp, it's a state university in São Paulo. We are divided through the whole state, so each city that appears here in this map has a campus of Unesp. Okay? This is why there is no São Carlos in this map, because São Carlos, there is no campus of Unesp. This is why. And this is our lab here in the campus. This is the entry of our university. So I think a lot of people has talking about glass for you this week, and then we'll continue to talk about glasses for the whole week. But I like very much this phrase, and because now we can consider that we are in the glass age. Okay, we have a lot of things happens in these last decades, and these last years also always related with the new applications and new ways to use glass. So this is quite nice. In 2022, the United Nations have chose the International Year of Glass. So in 2022, have a lot of conferences and different celebrations around the world concerning glasses. So it's very nice for us also that we work and live with glasses. I just put here some definitions and the most actual definitions from glass ceramics, and photonics that is related to what I will talk with you today. So the definition of glass, this is a quite recent paper in Journal of Non-Crystalline Solids. Our main guest here, Edgar Zanotto, participate of this last definition. So glass is a non-equilibrium, non-crystalline state of matter that appear solid on a short time scale, but continues to relax towards the liquid state. This is one of the definitions of glass. Also, for glass ceramics, it's a quite nice and quite new definition. It was also given in 2018. Edgar also participated of this paper. He's also in this paper. So the definition of glass ceramics. Glass ceramics are inorganic and non-metallic materials prepared by controlled crystallization in glass via different processing methods. They contain at least one type of functional crystalline phase and a residual glass. The volume fraction crystallized may vary from ppm to almost 100%. So it will be useful for us, these definitions, during this talk, because I will talk about glass, pure glass, I will talk about nanoglass ceramics, I will talk about ceramics and glass ceramics. And of course, the definition of photonics. So photonics encompasses the technologies, devices, products, and processes that generate, transmit, transform, and manipulate light in any format, color, or location. It combines classical and quantum physics, semiconductor, waveguides, nano and bulk optical engineering, and materials innovation. So these are some nice definitions to start this talk. I really skip all the basic about glass because I think we have heard about this week. So I would jump directly to how to prepare optical glasses. So the main technique we use in the lab to prepare optical glasses is melting quenching. It's the most common one. It's the most used one in industry and in research labs. This is the most common way to produce optical glasses. So we start by weighting the composition, okay? We homogenize this composition. We can use, for example, one mortar like this one, so we can do it by your hands, but we can also use some equipments that can mix much better the compositions, and so after melting and have the glass, we have a more homogeneous material, okay? So we need to choose different crucibles because it's different from silica, that it's the most known and most used commercially glass. The glass that we will talk with you today, this non-conventional glass, usually they also react with crucibles. So we need to choose the correct crucible to different glass compositions. Okay, so we need to choose the best one for each composition. So we melt the glass, we refine during some times, we quench it in a given temperature. It will also depend on the composition of the glass. And then we are annealing to release thermal stress caused by thermal quenching, the stress, and then we polish the glass. Okay. Oops, sorry. However, depending on the application you are intending, and it depends, of course, of the composition, we need to use different synthesis methodologies, okay? So Andrea told us before about the Gorilla Glass and also the very thin glass used to cell phones or bendable glass. So in this case, we can use this kind of furnace. It's called contactless melting. So there is no contact with the glass. And then we can prepare very thin sheets of glass that can be bendable later. So some glass compositions can be prepared from sol-gel process. It's different from melting quenching process. You don't need to heat too much the glass. We can prepare from solutions. Sputtering, it's a technique that can be used to do some thin films or some special coatings on glass surfaces. I will show you some applications about the sputtering today too. Aerodynamic levitation is a very nice technique, but for instance, it just allows us to prepare very, very small pieces of glass. But one interesting thing is about aerodynamic levitation. You can prepare very compositions that are really quite complicated to transform from crystal to glass. So by conventional technique, by melting quenching, the quenching temperature, the decreasing temperature that we need to transform from liquid to solid should be very high. So some compositions does not attain this quenching rate so fast, so you cannot produce it using this conventional technique. So this is why you use, for example, aerodynamic levitation, because you can heat the glass with a laser, and then the temperature is heating very fast and very high temperature, and then when you cut off the laser, the temperature will decrease really, really fast, and also you have very high quenching rates, and then we can prepare some very specific glass compositions. So Andrea told us also about the optical fibers. I will talk a little bit more about optical fibers too. And so the main process to produce the glass for optical fibers is chemical vapor deposition, because using this technique you can achieve very, very, very high purity compositions. So impurities, as Andrea told also, it's quite a problem in this industry. So we need to avoid them in the final glass. So the best way to produce optical fibers with the lower attenuation is using chemical vapor deposition. And for some special glass, for example, metallic glass, we can also use multi-spinning process. So, concerning the glass ceramics, we can produce glass ceramic by basically, we have more ways to produce, but basically using two techniques. One of them is controlling the thermal treatment. So you produce the glass, then you can treat the glass thermically above TG for a given time, okay, and a given temperature. Of course, we need to establish these temperatures, the best temperatures to produce these glass ceramics in the lab, and then we can control the growth of the crystals inside the glass. There's two ways to do that, and there's two main different processes governing this crystallization. One is homogeneous crystallization, another one is heterogeneous crystallization. So if you have homogeneous crystallization, that's most part of the time is the most important and interesting for application, we can do using two different ways. So we can put a nuclei inside, and so use this as a start point to crystallize, okay? Or your composition will crystallize by themselves alone, and you can have also some homogeneous crystallization from the glass. Okay, and the second one is by controlling the cooling rate. By controlling the cooling rate, this is something that we'll talk a little bit more about this today. It's when you prepare a supersaturated system, so very small, very little special compositions. When you melt it, you melt the glass, and then we have some chemical components inside that can be as a supersaturated solution. What it means? So this will be soluble only at higher temperature. When you decrease the temperature of the melt, there is some crystal that will appear. So specifically for some compositions, we can have very, very nice glasses and crystals inside that we can also later put out of the glass and use these crystals for other applications. So, fortunately, Andrea gave us all the background about optical properties. I don't need to talk about this. I would just jump directly to what kind of chemical components we need and we use to prepare glass. Of course, depending on the application. Okay? We have, from the books, we can find this table. This is from this Varshnaya books. So we can find here elements that can be transformed in glass. This is the main forming elements, okay? So in oxides, sulfides, selenides, tellurides, halides, nitrates, and so on. There's a lot of them. And of course, we can combine them with a lot of elements. So it's almost, the possibilities of compositions is almost infinite, okay? So always, as I will talking about optical properties are really related to which wavelength we need to use and want to use some different glass. And for this reason, we need to choose the components of the glass to use this and to use them in different wavelengths. So for example, here is a sketching just for about the transmittance of silica glass, for example, that is the main user for optical fibers. We have here heavy metal oxide glass, that we'll talk a lot about this today. Fluoride glass, sulfide glass, selenide glass, stellaride glasses. And so the transmittance window will change depending on the composition. So, but why, when you show you this, this figure here, this is here, why the transmittance will decrease depending on the glass that we are using? The main reason is what Andrea told us today. It's because it's due to the problems related to the refraction index. So depending on the higher is the refraction index, higher will be the reflection, for example, that we have in the surface of the glass when you shine the light in this glass and you want to see something that goes out on the other side. So the reflection, it's dependent on the refraction index. So if you increase the refraction index, the transmittance of the light will decrease. So this is really, refraction index is really the most important property to optical glasses, okay? Of course, we have other effects that can happen when you shine light in a glass surface. Andrea also described all of them. So for us, the important is, of course, related to the refraction index. I will talk a lot about heavy metal oxide glass that present refraction index close to 2, for example. So the reflection will be important, okay? And also, the absorption will be important. So the purity of glass, the contaminants that we probably have in the raw materials will influence in the optical properties. So we need to take care on this too. I will talk a little bit about scattering, because some of the glass we are interested in is nano glass ceramics. So we need to control the size of these crystals to have good optical properties. And just relate to the question that Serbena made for Andrea, usually if we have nanoparticles inside the glass, to avoid a lot of scattering, we need to manage the size of the nanoparticles below 100 nanometers, if we need to avoid a lot of scattering, okay? So, in fact, if we need to take advantage of the nano size of the crystals, we are going to work around 20 nanometers up to 50 nanometers, and so we can take advantage also of the nano size of the crystals, okay? So let me see if it's work. Should work. Yes. Just to introduce you, now I'm just talking with you. All of our world is connected by fiber optics, okay? So we can just, now we are in online, so we are transmitting this talk. And so how people in Japan can, at the same time with us, following this presentation? The only way is optical fibers, okay? So today I think it is one of the most important applications for us. We are connected 100% of our time. We are connecting cell phones and computers. We are connecting by our watch. We are connected all the time. And so this is what make this possible. It's optical fibers. Okay? So optical fibers is at least expensive, most reliable method for high-speed and long-distance communications. But you have some challenges even today, concerning the optical fibers, we are continually improving the properties of optical fibers, of different materials, to make it some broader bands, to put more information, to increase the speed of the transmission of data. So to achieve this kind of use of the optical fibers, you need continuous improving the properties and, of course, developing new materials and new compositions. Just to give you an idea, for those that never saw this map, this is the map. All these small lines are optical cables that are connecting all the countries. This is submarine cables. So this is submarine optical cables. So can you imagine the amount and the length of these cables? We can go and back to the sun several times, okay? So it's really, really a lot of optical fibers that are using today. This is the US network connectivity map. This is the Brazilian one. Here in this place here, of course, for those that study geography before to come to Brazil, why we don't have a lot of cables in this part? It is the Amazon, thank you. You did your homework before. And so this is why we don't need a lot of optical cables for monkeys or something. So this is why there's not so many cables in this part of the country, but in the coast here, where the most of Brazilian cities are, so we have a lot of optical cables too. So how does it work, the optical fiber? So an optical fiber is composed by two different glass compositions, one in the core and another one in the cladding, okay? So in the core, we have a glass with higher refraction index, and in the cladding, a very close composition from the core, but with a little lower refraction index. And why we use this? As also Andrea told us today, we need total internal reflection to conduce light inside, to guide light inside the optical fibers. So this is why we improve the amount of light inside the core and decrease the loss when you need a lot of distance. We need to travel this light through a very, very high, long distance. So for example, if there is an optical fiber comes out from Japan and come to Brazil, we needed, I don't know, 10,000 kilometers of fiber. So we need that the loss of this fiber will be very low, and so all the scattering or possibilities to lose light that is confined inside the core will be also very low, okay? And then we put some plastic coating, okay? That is usually PMMA, so it's a polymer, it's quite common one, okay? Polymethyl methacrylate. It's also it's the most used in the industry, but for special applications we can change the polymer because for some applications we need some different polymers. This is an optical tower used to produce optical fibers, of course. I would just put this here just to have for those that never saw this optical fibers have an idea. In Araraquara we have an optical fiber. It measures 7 meters of height. So we have all these components. So it was a tower used to produce silica-based optical fibers. Today, we adapted this tower to produce low melting glass. So we need to change a little bit the components, but it's worked very well. So this is the three main kinds of optical fibers that you can find in the market, in the literature. The first one is the single mode step index fiber. This is the most known for optical communication, okay? And This is also something interesting because the wavelength of the light transmitted by telecommunications is 1.55 microns, as Andrea told you some time ago. And will be important for the discussion later. So for some applications, we don't need single-mode fibers because single-mode fibers is quite complicated to prepare. We need multi-mode optical fibers. It's a little bit more easy to produce, but not less important for a lot of things. And also we have a very different, we can change the size, the relation between the size of the core and the cladding, put in 2 claddings, put in 2 cores, put in 3 cores, put in different things inside the glass. So there is we can stay here and talk about more than a week about different kinds of optical fibers, and it's a lot of things. And as I told you, one of the main important things here is to be considered is the refraction index of the glass. So the refraction index of the core must be a little bit higher than the refraction index of the cladding. Usually 10 to minus 3 is enough to guarantee the confinement of the light into the core. As I told you, there is some very different types of fibers. These are the photonic fibers. They are much more complicated fibers, much more difficult to produce, but it exists. We can buy it. You can go to the Torlab site and you can buy it. So it's available commercially. Of course, each one has a specific application, but it's available commercially. So just to have an idea, an optical fiber is twice the diameter of a human hair. So it's a quite small piece of glass, very, very tiny. So of course it's fragile. So this is why we just put some cover on plastic to give it a little bit more mechanical, to increase the mechanical properties of the glass. Okay, it is interesting when you talk about silica glass because for bending it is quite fragile, but if you stretch, it's not fragile. It's quite strong. Okay, so it's quite nice too. So as I told you, we use internal reflection to conduce the light into the optical fiber. So this is the example how we do that. Okay, so we need to input the light in a given angle. So as Andrea also explained, so depending on the angle, after the critical angle, the light will be guided inside by internal reflection. Okay, total internal reflection. This is how we use to input light into the fiber. Okay. So, but what is important when we talk about glasses and glass for optical fibers? This first graph here shows the loss for different kind of fibers. So this is silica fiber. So the loss in the silica fiber will be lower at 1.5 microns. Great, because 1.5 microns is the wavelength that we can produce the fibers to increase the signal into the fiber. That is the erbium doped fiber. Okay, so I'll talk a little bit more about this also. But we have other kind of fibers, for example, fluoride fibers. Fluoride fibers are, should be the fibers when you can achieve the lower loss theoretically, but in practical it's almost impossible. Okay, it's quite difficult to produce fluoride optical fiber. There is 2 or 3 companies around the world that are producing this. I would just talk about this also later. And so this is some compositions used to prepare these multimode or single mode fibers. These are the preform. So Before to produce the fiber, we need to produce a preform. Okay, there is many techniques to produce preforms. As I told you, for telecommunications, the most used is CVD, so the chemical vapor deposition. This is the best one because we can avoid almost 100% of water. That is what produced this loss here in 1.5 microns. So if you have water that will absorb exactly in this wavelength. So this is why you need to avoid water into the fibers. So this fight from glass makers and water, it's a continuous fighting. It's almost impossible for some compositions to avoid water into the composition. Okay. So when you have optical fiber, so we input the signal into the fiber. Okay, there is a lot of connectors. Here is a splice or a connector, or the fiber has a length, for example, 200, 300 kilometers, and then we need to solder connect it. Thank you. To connect two fibers. Okay. So of course, when you do that, we have some defects on this connecting point. So we have some loss. So after some kilometers, this signal will decrease. So you need to increase this signal. Okay. So to increase the signal, we use optical amplifiers. And so the best one to telecommunications is the erbium doped silica glass. Okay, why that erbium? Because just show here, erbium will emit light exactly in 1.5. Okay, so you have the loss, the minimum loss of the silica fiber with someone that is emitting light in this wavelength. So it's the best word for optical, for silica. How does it work? How does it work, the optical amplifiers? So we have the silica fiber arriving here. We have here another fiber. It's a fiber doped with rare earths, usually 50 kilometers. Each 50 kilometers of fiber, we need to put an amplifier. Each amplifier costs around $10,000. Okay, so you can imagine for all the fibers that we have, how much money we can do with optical amplifiers. Okay, so these optical amplifiers work. It's almost in the same way that Andreas explains. So we have a continuous laser pumping this fiber, so the electrons not stay on the lower level, but they will stay in the upper level here. So when the light comes in, this will stimulate the emission of these electrons. So the electrons come to the ground state, and then so they emit light at the same wavelength, and then at the end of the fiber, we have an increase of signal. This is quite simple way to amplify light. So as I told you, this is the brothers Poulain. They discovered the fluoride glasses in March of 1974 in the University of Rennes in France. This year, they celebrated 50 years of the discovery of these fibers. And it is quite nice because I did my PhD with these guys. And when I was in France, I knew that it was the fluoride glass was discovered in March of 74. It was exactly the year was where I born. And I asked them, when? What the day? I don't know exactly. I didn't remember. But this year, when they celebrate the 50 years, the day that they opened the ceremony to celebrate, it was 11 March. That it's my birthday. So great. It was, unfortunately, I could not be there, but it was really nice. I saw some pictures. I received some pictures. It's quite nice. So the glass, the fluoride glasses are quite difficult to do. This is the main problem to produce in a very large scale. There is some trick that no one knows, only few guys. So 3 guys are in the Verfleuré, that is the enterprise founded by Marcel Poulain, that is in the market today. In the market, they sell fluoride optical fibers. And another guy is one guy that works in fluoride in Verfleuré, that goes out and opens his own company that today was sold to Tor Labs. So Tor Labs sold. You can buy fluoride fibers from Tor Labs, but it in fact comes from the same lab that the Verfleuré. So this optical fiber, they present very, very low transmission loss in the infrared. That is some region, that is a region that the silica glass cannot be used, because silica glass, we're going to use up to 2 or 3 microns. Okay, so if you need to go further into the infrared, you need, for example, fluoride fibers. Okay, for the most known fluoride fiber, that is Ziblin, it is zirconium-based fluoride fiber. They can achieve 7 microns in transmittance. But there is some fluorindate glass that can achieve up to 10 microns. Okay? So they can be used in lasers, in the infrared. They can be used for optical amplifiers. And the last applications is some components that is using in the ExoMars mission to detect CO2. Okay. We can also have chalcogenide-based glass. Some of you come from some very nice labs in the world that's working with chalcogenide glass, but the same university in Rennes, in France, are also a very nice group that works in these chalcogenides. Okay, this is the preforms used to produce the chalcogenide fibers. This is a sulfide one, a telluride one, so this is black glass. Because I'm not interested in the visible range, I'm interested in the infrared. So in the infrared, there is no problem. Okay? And why this glass could be used to produce lens to see in the dark? As Andrea told us today, you can use a trick then, you can dope it with the hertz, and then the image that you're going to see in gray scale in the infrared can be passed by up conversion. You can see in the green, for example, so you see a colored match, but usually it's in the gray scale, okay? Because this is also used for optical fibers to detect the CO2 lasers. I don't need to say to you what's the importance to control the CO2 nowadays, okay? It's quite important in all industries and around the world concerning the greenhouse effects, okay? Not only CO2, but another gas. So our body emits lights at 9.8 microns, okay? So everybody emits light at 9.8 microns. So silica cannot see in these wavelengths. Fluoride fiber cannot see in this wavelength. They absorb this light. So the chalcogenide glass are the only one that can transmit this light at 9.8 microns. This is why they are used to produce lenses for this way, okay? So what about heavy metal oxide glass? So I'm quite not really nice people to say what is the disadvantages of heavy metal oxide glass, because I work with them now my whole life. It's 30 years I'm working with glasses, and I work with heavy metal oxide glass. I pass a little bit fluoride, chalcogenide, mixture of them, fluorides, fluorophosphates. Not only, I just not work with the silica-based glass, but the whole family's concerned glass, I think I'm work. And they present a lot of advantages, okay? They can have a high refraction index that, of course, for some applications is quite important. They present a high nonlinear refractive index, good Hurd solubility. So when you are talking about luminescence, or we need some emission, so it's nice to have the solubility, because silica is not a good glass to host, to receive Hurds, in fact. So low photon energy, so depending on the composition, it can achieve 7 microns in transmittance, high thermal stability, relatively low melting point, of course, depending on the composition. Easy preparation, I mean, concerns some chalcogenide and fluoride glasses, heavy metal oxide glasses, much easier to prepare. Of course, there are some disadvantages, so, but I left to you to think about some of them. Price of some Hall components is quite important in this. If you need to produce glass using germanium oxide, this is not the good moment for you, because germanium oxide, it's a very nice, important component to produce chips, okay? And so the price has increased a lot. So 1 kilogram of germanium oxide today, it's around $5,000. So it's not really, we cannot compare with silica, okay? So I will just talk a little bit about the optical properties of glass ceramics. So last year we have the Nobel Prize in chemistry in the quantum dots, okay? So this is quite nice for us, that we work with glasses, we work with glass ceramics. It was also one kind of reconnaissance of the work done in this field. I just put here one application that is the QLED TVs or screens that we use today, but there's a lot of applications using nanoparticles and quantum dots or metal nanoparticles inside glasses. So as Andrea told you this a little bit later, we take advantages of the superficial plasma resonance of the metallic nanoparticles inside glass. Metallic nanoparticles, when they are very small, they are very in the nanoscale particles, they can interact with light and absorb light by the oscillation of the electrons on the surface of these nanoparticles. So this will depend on the size of the nanoparticles. They will depend on the nature of the nanoparticles. I just put here some silica doped with silver, okay? This is boroaluminate glass doped with gold, and for example, silica doped with copper. So we can tune the absorption wavelength of the nanoparticles by change the nature, but can also change this. We can tune this energy of absorption by tuning the size of the particles, okay? So we can control the growth of these nanoparticles inside the glass and then tune exactly what's the region they will absorb. There is another very important property here is refraction index, because this, for example, for silver, this absorption here of silica in 420 nanometers is because silica has an refraction index around 1.5. If you take a glass with refraction index with more or less close to 2, this absorption will shift to the visible, to the green. So they will absorb the green, and then the glass will appear red, usually. So if transparency in the visible is important, we need to play with the refraction index too. Otherwise, we cannot use these properties of these particles, okay? So with this, I visit the museum this year too. So I took this glass. In my mind, it was a very small cup like this, and in fact, it is a very big one. So it is quite nice. I saw it in the... So how use these properties of the nanoparticles? For example, if you have a glass, we can take advantage of heterogeneous crystallizations, for example. In this case, we prepare a glass doped with silver, and when we treat it thermally, the silver will move to the surface of the glass and crystallize on the surface. Okay? So for some molecules, we can use this effect for Raman amplification, for example. So many kinds of molecules has very small signs in Raman, for example, Raman scattering using this technique. And so when you have a surface like this one, with the nanoparticles on the surface of the glass, the organic compound, for example, can be attached to this surface, and then the signal of the Raman will be increased. And sometimes can be increased 10 to 5 times. So the absorption will be much better. And you can use Raman, that it's a very easy and nice and easy methodology to study these materials, to verify the existence of a very, very small quantity of, for example, in this case here, we show that the surface could be used to detect some medicines. Okay, so it's in a solution of 10 to minus 6 mol per liter. So it's quite nice. So we can also use nanocrystals, nanometallic crystals inside glass to get white light emission. The size of in this paper, we produce some glasses just controlling the amount of silver inside the glass. And before to become a crystal, we have some nuclei, okay? And depending on the size of the nuclei, the emission of silver will be different in the visible range. So if you can control the size of the nuclei before to have a particle, a really particle with a nanometer, we can in fact have different emissions. In this case, we could tune from blue to white. This is the emissions here. Just change the excitation wavelength, because for each excitation wavelength, we will excite different size of clusters. And these different size of clusters will present different emission. Okay, so you can tune and use this property. This is another one. We did the same, in the same direction. We controlled the size of the nanocrystals by changing the composition. And in this study, we had a composition that present a very good white emission. And then we use another technique that is laser writing, okay? So we can, using femtosecond lasers, we can inscribe a channel inside a glass, not on the surface, but in the middle, below the surface, by controlling exactly where will be the focus of the laser, okay? So controlling the power of the laser, the speed that you're gonna write in these wavelengths, these waveguides, we can obtain very nice waveguide like this one, and then we can find this is the measure of the light when you shine here an UV light. So we excited this waveguide with the UV light, and then we saw the white light comes out at the end of the waveguide. So we can control and also guide, generate and guide white light into the channels. I don't know if you saw, but in the media some weeks ago, there was released the first optical chip. That is a Spanish company that is work on this. So we don't need any more electrons inside, just light. So this is kind of waveguide that we need to control where the light is going to be inside the chip. And then this is really nice, something that A lot of people talking about many times ago, many years ago, they start to talk, and now we start to see this kind of applications in the market. So this is another way when you need to put some other properties, not only optical, but in this case we were interested to put some magnetic properties inside the glass. Magnetic properties is kind of problem because the most magnetic elements are the transition metals, but all of them are colored. When you put nickel, cobalt, or iron into the glass, they become very, very colored. So we lost the optical transmission in the visible. So one way is to produce magnetic nanoparticles, in this case was iron oxide, to cover the particle with a shell, for example, silica, and then redisperse this shell, these nanoparticles, into a glass composition. And then if no ion goes to the glass, we can achieve transparent glass in the visible with magnetic nanoparticles inside the glass. Okay, so this is what we did. We prepared the nanoparticles, then we covered with the shell. This is a big nanoparticle. So the size of the nanoparticle with the shell is 100 nanometers, and then we put them into the glass. Here we can see the glass has no color. It was 8% in mass of silica and the magnetic nanoparticles inside the glass. Just jump a little bit here. So we can also control the emission, or can increase the emission by putting together metallic nanoparticles and rare earths. So a lot of people discuss on the literature how we can improve the efficiency of the rare earths inside, for example, an amplifier, because we need more powerful devices, more power to put light into the guide, into the fiber. I have a lot of data to transmit. And so how we can improve this? So this is one possible way, is to co-dope the glass with rare earths and the metallic nanoparticles, and then try to transfer energy from the nanoparticles to the rare earths, and then increase the efficiency of emission. Okay? This is some basic study that we did in our lab. As Andrea showed us, we have the UV-Vis spectrophotometer, and we put a furnace inside the spectrophotometer where we can take we can treat the glass and take the absorption spectra in situ during the treatment. So otherwise we need to treat the glass in the furnace, you put it out, you do the measurement, you put again into the furnace, you put it out, you do it again, and then in this case we do the treatment inside the equipment we did some treatment for 72 hours because some glass, the crystallization were very, very slow, very slow, and so we can do that using this approach. So this is just to how to do that? No? Okay. I can show you later. This is a small movie. So I'm going to shift now to magneto-optical materials. This is one of the main interests of our lab today. We are going to do two different approaches for crystals, magneto-optical crystals and magneto-optical glass. But the magneto-optical crystals are prepared using glass. So this is the important thing here. We have some, so we can use glasses to study magneto-optical materials. We can study glass ceramics, optical fibers, hybrid materials. As I told before, we can produce nanoparticles or magnetic nanoparticles and then redisperse these nanoparticles inside glass. So I call this a hybrid material, not really glass ceramics. Thin films, and of course, crystals that are the most used on the market. Why to use and study these magneto-optical materials? Some of the main important applications are for signal transmission and modulation, fiber optic current sensors that I'm going to show you also some. Here we produce some sensors like that in our lab. So inside these devices we have glass. So they are sensitive to changes in magnetic field and electric field. So we can use this to monitor some magnetic networks, or can use this to control or to follow what happens, for example, in a electric transmission line. Okay, so if you have some problems, these materials are very, very, very sensitive to changes in the magnetic field, so we can use this. We can also integrate this device with intelligent life, deep sea and deep space, weak field detections, help the warming of geological disasters, of course, because if you have, for example, a volcano, and that is the lava will be constantly change, and sometimes this will change also, sometimes not. It's really, it happens when the volcano will be in eruption. We have the lava movement, so it's change magnetic field. So if you have some possibilities to detect this change, this small change, this will be really nice too. And of course for health, because this device can be so sensitive that you can monitor, for example, your heart rate. You can monitor your brain with them, okay? So for magneto-optical effect, we use the Faraday effect. It's very simple equation. We have the angle of the light that will be changed when the light passes through a medium when you apply a magnetic field. So the angle of the light will change. So in this equation we have V. Here is the Verde constant. That is something intrinsic to the material that you are studying. B is the magnetic field. L is the length of the device that you are using. So why it's important for us here? Because to achieve a very, very high sensitivity, you need, and to measure, for example, very low magnetic fields, that is, for example, in the brain, you need a very sensitive material. So how to achieve this very sensitive material? You can increase the V, or you can increase the L. You can increase the V, but using glasses, we are limited by some chemical nature, okay? But we can increase the L. How increase the L? We transform the glass into fibers, and then we increase the L, okay? So we can play with these properties to obtain devices to measure up to 10 to minus 15 Tesla. That is what happens, the change in magnetic field that happens in the brain, for example. So there is some, when you go to the lab and try to produce different materials, we have some limitations because magneto-optical glasses, we can produce very high materials with very high Verde constant using iron or cobalt. But as I told you, they are colored, so in the visible, it does not work. Okay, so you can use some hertz, but hertz are it's a quite nice elements, but they are also quite complicated to put inside glass. So there are not so many compositions that accept very high quantity of hertz. So we need to play with them and try to increase the amount of hertz inside the glass. And why this is important, I'm going to show you. So the first application here, we start with this glass, and of course, I have no shame to say that it was an accident, because I was interested in this composition because this is a heavy metal oxide that could be used to prepare glass to up to 7 microns in the infrared. So I was using this glass to produce glass to operate in the infrared. And then one student of mine came to me and showed me this picture. I have a problem. I have a cubic crystal inside the glass. See? Of course, come back to the lab and do it again. And sometimes later, he comes and shows me again the same picture. I have the same crystals. Something's wrong. Or not. So now we are playing with the composition of this glass and producing crystals using the supersaturated method that I told before. Okay? So depending on the amount of hertz that you put inside the glass is quite stable. The Tx minus Tg, that was parameter that we use to stability of the glass, is around 250 degrees. So we can easily use this glass to prepare optical fibers. But when you put 1 or 2% of hertz, it's completely destabilized. There is a formation of a crystal. But okay, it's quite nice. What is this crystal? What is the composition of this crystal? And then we start to study this. So we could see that this is a mapping in 3D of the crystal using Raman spectroscopy, but in this case we use microluminescence that we can also use, and we can also have this information using Raman if the laser that we are using to see the crystals, to measure, to make the Raman spectroscopy, it's the same laser that will excite the crystals inside, or the elements that inside. So you're going to see the emission that is much, it's orders of magnitude much more efficient than the Raman one. So this is why you can see luminescence. And with the size of 1 micron, that is the spot of the Raman, we can do a 3D mapping. And so this image was done with 206,000 spectra. So it took 3 days measuring in a very nice equipment in France. And after that, we could put all the spectra together and so. So where the red light is coming, it's where the hertz are. So in this case, it's quite interesting because there is a void inside the crystal. Okay? The crystal is not well formed. But okay, this was the first one. This cube was doped with erbium and ytterbium, the most used pair to up conversion in optical materials, the most studied at least. And then in this figure here, when you shine light with the laser, here, when you shine light in the laser, this is the image in the microscope. You can see the green light comes out. So this is the emission of the crystal due to the up conversion of erbium. This is it's optical, the Raman microscope. the micro Raman microscope. So when you try to understand what crystal are forming, we arrive at this one. It's a gallium garnet, and it is quite nice. Why it's quite nice? Because gallium garnets can also present magneto-optical properties if you dope the crystals with the correct hertz. So we did that. We put terbium, and terbium is the component of TGG, that is the terbium gallium garnet, the most used crystal in telecommunication for optical isolation. Okay? So we substitute the erbium and ytterbium in our matrix by terbium, and then we produced TGG. Okay? This is the crystals obtained, used. We can now control the size of the crystals from some microns to 200, 300 microns. Okay? These are single crystals. We study them. Depending on the way, depending on how you prepare the conditions, they can be polycrystals. But if you control correctly the preparation, we will produce single crystals. Okay? And okay, nice, we have TGG. Okay? This is something that we are studying now. So we have TGG, holmium GG, dysprosium GG, gadolinium GG. We mix all of them. We have a lot of crystals. Okay? These are some images from these crystals. Okay, so we have gallium garnets, but one of the most known is aluminum garnet. And if you change aluminum, gallium by aluminum, what's going to happen? It's work too. We can have, with this, we can have aluminum garnets with the hertz. And this is the nice thing about this system. You put it all together, it's almost to cooking. You put all the furnace into the furnace. You just control the speed of the quenching, and then the crystals will be formed. Okay? And the amount of hertz you put onto the composition, we will find inside the crystal. I don't know how it explains magic, but sometimes magic also happens in science. A lot of time in the lab makes some magic happen sometimes. Okay? So, as Andrea told also, exactly the same. We can change, when you can change, for example, for luminescence, when you have a lot of hertz, it's not good. But we can control, for example, the amount of hertz, and you substitute to form the composition, to form the garnet, you put yttrium or scandium, and just a small amount of the hertz if you want. And then the emission of these crystals will be much, much better than in glass. This is what we are exploring now. And of course, for each composition, we have different conditions to prepare it. Okay, so this is the terbium aluminum garnet. Okay, this is one crystal with more or less 40 microns. Okay, this is gadolinium garnet. This is terbium garnet. And the most interesting, we can dissolve the glass and take the crystals. It's quite nice. So I can use them into the glass if I can control the size, obtaining very, very small crystals, but I can also take the glass and take advantage of the glass outside of the crystal. Okay? So one possible application is use these garnets, for example, to develop some sensors in the infrared. Nowadays, there is some chalcogenide glass doped with hertz that are using, for example, to detect CO2 or other molecules in the extraction of petroleum, for example. Okay? The main problem is the emission of hertz inside glasses are large. Okay? So, and the absorption of gas are much times very close one to each other. So if you use crystals, we can make this emission much narrower, and then we can tune with more precision into this gas. Okay, so this is one. This is the window and transmission in the infrared. So we are now interested in this CO2 absorption. So moving to magneto-optical materials, and in this case is glass. So as I told you, we were interested in TGG. Why TGG? TGG is the crystal used, for example, in the LIGO This is the Laser Interferometry Gravitational Wave Observatory, where they detected the gravitational waves. Thank you very much. Okay, so the optical isolators in the interferometer of the LIGO is use TGG. If you enter into the site of LIGO, you see, because it's an open lab, you can see that one problem is the crystals have some problems with temperature. They increase the temperature. When you work with magnetic things, temperature is not good because the efficiency will decrease. So if you can work with a glass that it's an isolator, it could be good. But we need to achieve the same, or at least close property in the Verde constant. So this is why we are using glass to study this. So the best one in this case is terbium, because the absorption. All of, for example, dysprosium and holmium are also much better, even better than terbium, but they absorb a lot in the visible. So this is why terbium is the best one. So we did some, I don't know, it does not work here. This is a small movie showing that the glass can be attracted by the magnet. Okay, and I can show you later if you want. We produce also some optical fibers, and the fiber is also magnetic, so it's not work, of course. Nope. We could measure, using these optical fibers, we could measure, for example, 10 to minus, using 10 centimeters of fiber, we can detect changes in magnetic field in the range of 10 to minus 3 millitesla. Okay, so if you increase the size of the fiber, we can achieve much more efficiency. And so with this, we open a startup. We are producing these materials today. Okay, so this is our company called Glass technology. So we produce some current and magnetic field sensors. We are studying different optical materials, including also optical fibers. So this is the device I showed you before. This is the device we have here. And also, the last thing I'm going to say, it's using these materials, we can changing a little bit, I'm not talking with it's an optical fiber, but it's a planar waveguide. So we call them ribbon fibers. So instead to have a cylinder preform, we can take a slice, like a glass slice, microscope slice, put in the tower and draw it. And then what do you have? We have a ribbon fiber. So it's something like that in this dimension. Oops, sorry. This dimension here. So you can control it. You can control the thickness of the fiber. And what is interesting with this, we can use a femtosecond laser to write patterns on the surface of these tiny fibers. Okay? So if you see here, here's the size of the laser here. The spot of the laser is 1 micron. So we can put a lot of information in the tip, on the tip of this fiber, okay? So it's something that we are also studying. And of course, we can use another technology. This is pulling. It's a thermal pulling. Thermal pulling, you take a glass, you apply difference of voltage on the surface. You take an electrode, and in this case, it's an electrode like this one. You can imprint this motif on the surface of the glass, okay? So in this case here, our collaborators did the LaVie electrode, okay? We input into the glass, and then this is an image of the second harmonic generation produced in the range where the pooling was applied. So there is an increasing in the second harmonic generation, and we can use this for some applications too. So this is another interesting thing, that Hurts are known by the stability of the NOx, the number of oxidation of the elements. But using this approach for terbium, we can induce the oxidation from terbium 3 to terbium 4. And this change of the oxidation changed completely the emission spectra. And then we did the same using this electrode. And here, when the electrode, in fact, is here, where you send blue, there is no emission. So it's zero emission. And in this, the middle of the square, so we have terbium 3. And here we have terbium 4. So there is no emission. So we can control where I can have emission in a device. So it's quite also nice. And of course, if it does not work expected, we did some artistic point of view of these crystals. Tiago's here is the guy that play with this in the lab also. So thanks, lab. Leo also is here. And just the last thing concern a problem, in fact, that not so many people talking about. We have a very big problem around the world that concern the death of birds by striking through the windows. So it's a billion birds per year. Just billion birds is the estimative in the United States and Canada. So there is not another estimation around the world, because just in the United States and Canada, in some place, I think in Germany, they have the technology to produce different ways to say to bird, look, I'm here, I'm a glass, I'm here. So, hello, don't hit me. And there is only 2 companies in the world that are commercializing this kind of materials, okay? And unfortunately, this is the silhouette of the bird that strikes a glass. It's from the internet, but this one, and you can see here the wings and the head of the bird. This is the wing. This is in the lab that I spent 3 months now in the end of the year in Portugal. I was in Abril as an invited teacher, invited professor, and we had this in the window of the lab. So unfortunately for the bird, but okay. So what can I do within that? So this is just something in the... There are a lot of birds that migrates from the United States, from Canada to the south of South America. It's a huge travel. And during this project, they can find a lot of glass in the... because usually they feed themselves on the cities. So that's the place where we have most problems, okay? And why it happens? It happens because birds don't see like humans. The main color that birds see is in the UV. It's around 350 nanometers. They also see in the visible, but the best wavelength for them is in the ultraviolet. Okay, so we need to develop something that the birds can see, but the architectures does not fight too much with us, because otherwise it's easy, just paint the glass. But when you say that for an architecture, you say, no way. The beauty of glass is the transparency. You can see inside, you can see outside. I want to put a color in the glass. I want to put something that you avoid people to see this beauty, that it's the building made of glass. So we did some studies here, and we developed a coating, an inorganic coating that can be produced by sputtering. You remember sputtering that I told you in the beginning? That is the same technique used for industry to deposit titanium oxide and make the intelligent glass that can self-cleaning glass. Okay, self-cleaning glass are prepared by a sheet of glass and a coating of titanium oxide on the surface. There is many other properties related to them. And then we did the same, but in this case it's not titanium oxide, because titanium oxide is not the best one to the bird, not to the application, to the bird. Okay? And so when you put it in the light, in the UV light, you can see here, this is the place without coating. And we can see here that it's transparent. And this is the place where the coating is. So the bird can see it. Okay? Now we are enrolled with the Brazilian government to develop some special laws here in Brazil, because there is nothing, but there is nothing around the world. There is only some places in the world that is some legislation about this, how to protect birds against this kind of strikes with the glass surface. And I think it's important for us as glass scientists to try to develop and mitigate these problems. So this is why it's something not really related to my magneto-optical materials, but it's quite interesting, and it was a challenge made by some companies here, and we developed it. Now it's in the way to make the patent about this. So what about the future? I don't know. Some people would like to go to Mars, okay? But even if you go to Mars, we need something there. We need some infrastructure, we need something. But one thing is important. We can prepare glass on the Mars surface. This is good, because the raw materials over there, it's not so different from here. So it's possible. But we need to develop a lot of things. We need to develop optical fibers, lasers. If you want to communicate with people in Mars, we need a lot of things. And all of these things are based on glass materials. Okay, this is quite nice. So this allows us to innovate, always innovate. Okay? But I don't know what's going to happen, but I took my place in the next flight to them. So I'm really interested in the miles. Our points earned here, 1.7 billion miles. It should be nice to travel on Earth after later, but I'm going to see. So I just finished my talk just to say, if someone is interested to work with this kind of glass, this photonic glass, we are places available in Araraquara, and master PhD, even for those that does not speak Portuguese. We have an international program in postgraduate, so, and for postdocs, chemistry, physics, and engineering you are all welcome. So this is our group in Araraquara, and thank you very much for your attention. Just the one thing, if you want to see some different glass, colored glass, uranium glass, erbium doped glass, europium doped glass, we have some samples here, we can play with them. Okay, thank you.
Oh, very nice. This is going directly to our glass museum that we are starting. We are starting at La Mave. Anyway, thank you. Very, very interesting question, and I'm really surprised and at the same time pleased that you started your own spin-off company.
Yeah.
You know, I always tell the students that you have several possibilities after you graduate. A researcher, you can go and work for an industry, but you can also set up your own company. You know, they're like the Park Tech, where we had the opening cocktail. It's an incubator for companies, and if you need a better space to incubate your company, we have here in São Carlos.
I know.
Anyway, Marcelo, just to start. I have a limited experience in trying to crystallize nanoparticles in glasses, very limited, but all the attempts that we did in our lab resulted in non-uniform distribution of nanoparticles, And yesterday I was talking to a student from Alfred University who met the same problem. So how did you solve this problem of getting a uniformly distributed nanoparticles in a glass matrix?
Well, for some compositions, we can melt and break the glass, prepare the glass, break the glass, melt again, break the glass, make it again, 2 or 3 times. It's mixing very well using the equipment. What's the name of the equipment? No.
High-speed mixer?
Yeah, the speed mixer. We have a speed mixer and a high-speed mixer. And the homogenation of the glass is really, really important. For some compositions, it's quite difficult. When you try to get only the first stage of the nucleation and the growth in very small particles, it can be work that is not so colored. But depending on the glass, usually when we work with a lot of germanium-based glass, it's quite difficult to have homogeneous. You can see that because the color is different. So the color is not homogeneous. When you see the glass, when you look on the microscope, it's okay, great. You have always the same size of the particles, it's great. But when you see the glass, the color is changing. So it's not easy. It's not easy at all. We do that. We prepare the glass 3 or 4 times, the same glass. And for some compositions, it works a lot.
Yeah, it depends a lot on the viscosity of
Yeah,
the glass. Right?
sure.
High visco glass it's a nightmare. Anyway, questions? Yes.
Thank you. Your talk was wonderful. I'm Anthony Secrekas from Lehigh University, and my question is related to the femtosecond laser irradiation you're doing to create your silver nanocrystals. Were you doing a heat treatment following the laser irradiation to grow the nanocrystals, or were they grown from the laser?
From the laser.
From the laser.
Yep.
And then how well were you able to control the size of the nanocrystals with the laser?
By the power, controlling the power of the laser. And of course, depend on the speed that you are writing, okay? So, of course, we showed the best one, but we did, I don't know, 3, maybe 30 different waveguides. And so we analyzed them later, but the speed and the power of the laser will play a very important role in the size of the crystals. In this case, in the white emission light, in fact, we don't have really nanoparticles. We just have clusters. When you have nanoparticles, the emission will be in the red for this glass. So to achieve the white light emission, you need to play with the clusters. So when you have 4 atoms, 5 atoms, 6 atoms, 3 atoms, each one has an absorption in UV. So you can play later with the excitation wavelength, and then you can see the white light emission. In that case specifically. But we use also to other compositions. And when you increase a lot the sizes, it's not really easy to control all the crystals.
Thank you.
Yeah, I am Professor Andrea de Camargo. I think you know me, but I have to identify myself for the YouTube recording. Marcelo, I wanted to ask you, what is the structure of the gallium garnet that is formed? Because you said rare earth ion goes into the structure, and I thought it was a cubic structure. So do you actually see reasonable intensity of the rare earth ions or not? Is it a distorted cubic or what?
They are cubic, and when you perform the luminescence of the crystals, we can see all the Starks levels, for example. The Starks levels. So they are really, really well oriented into the crystal. No, it's a perfect cube. But there is different sites into these garnets. They not occupy just one kind of site. There is one or two different sites. We measure here with in the physical department with Javier. We measure the X-ray of the crystals. We have the position of all the atoms. It's and it works very. Only dysprosium is not good. I don't know why. We don't understand why. We have very nice crystals on dysprosium, but the luminescence is awful. But for all other crystals, we put all the hertz inside. They emit. You can see the stark levels.
Okay, I think we should, well, one last question then before we wrap up.
Thank you for the talk. I'm Daniel Vasconcelos from the Federal University of Uberlândia. You mentioned the glass fibers being used as sensors to detect magnetic field variations to possibly detect earthquakes and volcanic activities. What's the order of magnitude of the land that you mentioned, that you can play with to detect the sensitivity you mentioned, and where would you place them?
The magnetic field of the Earth is 10 to minus 6 Tesla. It's a micro Tesla. So, of course, you have to develop something that will be much more sensitive than 10 to minus 6. It's not easy because, in fact, we can do this with this. I say we can do that. The researcher can do that. We don't do that, okay? We don't have this kind of fibers in our lab, or at least for the fiber that we have, we didn't measure this kind of sensibility. One way to achieve this sensitivity is doping the fiber with magnetic crystals, because the magnetic moment of the magnetic nanoparticles are at least 3 times, you can reach 3 times higher than the ions. So in this case, we can achieve a very, very, very small, high sensitivity and detect small fields. But for this kind of fibers, we are inquired for a company from the United States that were interesting and developed some fibers for applications, but they were interesting in this range of wavelength, in sensitivity, 10 to minus 6, okay? And we are doing work with them, and it's possible, but we need to prepare, I need to measure it. But one way it's increase the amount of hertz, because when you increase a lot, we forget about the optical properties because it's terrible, but for the magnetic properties, it's good. And the optical fibers to measure magnetic field changes in electric lines, it exists already on the market, okay? But they use silica fibers. And the silica doped just with a little amount of hertz. So the sensitivity is very low. So this is why they use at least 50 meters of fibers. So if you have our fiber that is 20 times more sensitive in the same wave, in the same length of the fiber, we can achieve a very, very small, we can measure a very, very small magnetic field. But I can imagine like this, one application, this direction to detect, for example, the earthquakes or something like that. It's known that the magnetic field changes, okay? So you can put a sound, another sensors to measure it.
So you haven't tried it yet?
It's just an idea. No, unfortunately not. Even to extract petroleum, for example, you can use magnetic sensors. You can use it in submarines. There is some applications in naval research in United States are developing some uses of this kind of materials to detect the presence of other submarines just by changing the magnetic field. Like sharks that can detect magnetic changes in the magnetic field with very high distances. It's almost the same principle.
Well, thank you very much. Final announcement. Everybody signed the list. If you did not, please do it, especially with registered students for credit. Just a final story about bird-safe glass. I have a small country house with a lot of glass, of course, and there's lots of birds, in the middle of the forest. So, and I'm a very poor scientist. I could not afford to buy, bird-safe glass, which is already in the market.
Me too.
It's already in the market. So how did I solve it? Just bought some inexpensive curtains. So I have curtains.
Me too.
And then you save this problem. You escape from this problem. But of course, bird-safe glass is a very, very hot and important topic, especially for this for buildings. Buildings. Anyway, you all have, if you are joining the tour, 1.5 hours for lunch, and then we'll meet in the hotel. I'm joining you for this tour because I've never been to this farm myself, despite the fact that I have been here for a few years. So I'll be joining you. And if you can, some sunscreen, because the UV is really high here. Unless you have a glass hat, UV absorbing glass hat would be nice too. Okay, see you then in a few 1.5 hours.
Now it's work, just a minute. This is the magnetic glass, okay?
That's it. Oh. Very good.
This is really work.
I want to ask you a lot more questions.
Yeah, sure.
Because my work is on, I'm trying to create germanium nanoparticles in my glass with femtosecond laser radiation, and I'm able to create them, and the goal being, instead of using it as a waveguide, to try to make them a conductive pathway.
Okay.
And so I may ask if later if I can email you later to try to schedule a meeting online. But the immediate question I just had is, for the modifications that I create, my question, at least the immediate question is, for my modifications, so we're looking down into the glass, I see a lot of refocusing occurring, but from your images, it appears that you only have one region where the glass was modified. Can you?
You are using femtosecond?
Yes. Yeah, I'm using the parameters are over here. So it's yeah, so I'm using a much higher repetition rate and lower speeds and energy. But do you think, because right now I'm starting to experiment with faster scanning speeds, do you think that would help mitigate the refocus?
We don't have the facility to write. It's a guy here in Houston, here in the physics class. He's a guy that we have cooperated more than 10 years. And they are specialists in making wave-guides with lasers. But with them, we use more than, I don't know, 10 different classes. And of course, it's not easy. In the beginning, you need to know repetition rates. I think I can show you something here. Let me try to find it. Just show you something here. This is uranium glass. It's a glass done with uranium. Oui. We're going to show you we did the thing more than 50 in this case, more than 50 projects. But clever is like here. Because it's
That would be wonderful.